Layered structure of atmosphere. It's the lower part of the atmosphere that has interested man from times immemorial. But from the beginning of the 20th century, when aeroplanes and radio were invented, the knowledge of the upper layer of atmosphere became rather essential. Much help was received in this difficult task of exploring this upper reaches of the atmosphere by weather balloons, aeroplanes, rockets, sound and radio waves, satellites of various kinds and Sputnik, etc. During the International Geophysical Year of 1952 up until 62, important discoveries were made about the atmosphere and many new facts came to light. 𝗬𝗏 de Bort, Sir Napier Shaw, Kennelly, Heaviside, Ferrell, etc. are some of the eminent weather scientists who have contributed significantly in the most arduous task of exploring the secrets of the atmosphere. Well, in this lesson, we'll be learning about the different layers of the Earth's atmosphere, modern views of the layers of atmosphere. The troposphere is the lowest layer of the Earth's atmosphere. Most of the mass, about 75 to 80% of the atmosphere, is in the troposphere. Most types of the clouds are found in the troposphere and almost all weather occurs within this layer. The troposphere is by far the wettest layer of the atmosphere. All of the layers above contain very little moisture. The bottom of the troposphere is at the Earth's surface. The troposphere extends upward to about 10 kilometers, 6.2 miles or about 33,000 feet above the sea level. The height of the top of the troposphere varies with latitude. It is lowest over the poles and highest at the equator. And by season, it is lower in winter and higher in the summer. It can be as high as 20 kilometers near the equator and as low as 7 kilometers over the poles in the winter. Air pressure and density of the air also decrease with altitude. That's why the cabins of high-flying jet aircraft are pressurized. The layer immediately above the troposphere is called the stratosphere. The boundary between the troposphere and the stratosphere is called the tropopause. Stratosphere. The stratosphere is a layer of the Earth's atmosphere. It is the second layer of the atmosphere as you go upward. The bottom of the stratosphere is around 10 kilometers above the ground at middle latitudes. The top of the stratosphere occurs at an altitude of 50 kilometers. The height of the bottom of the stratosphere varies with latitude and with the seasons. The lower boundary of the stratosphere can be as high as 20 kilometers and near the equator and as low as 7 kilometers at the poles in the winter. The lower boundary of the stratosphere is called the tropopause and the upper boundary is called the stratopause. Ozone. An unusual type of oxygen molecule that is relatively abundant in the stratosphere heats this layer as it absorbs energy from the incoming ultraviolet radiation from the sun. Temperatures rise as one moves upward through the stratosphere. This is exactly the opposite of the behavior in the troposphere in which we live, where temperatures drop with increasing altitude. Because of this temperature stratification, there is little convection and mixing in the stratosphere. So, the layers of the air there are quite stable. Commercial jet aircraft fly in the lower stratosphere to avoid the turbulence which is common in the troposphere below. The stratosphere is very dry. Air there contains little water vapor. Because of this, few clouds are found in this layer. Almost all clouds occur in the lower, more humid troposphere. Polar stratospheric clouds are the exception. Polar stratospheric clouds appear in the lower stratosphere near the poles in winter. They are found at altitudes of 15 to 25 kilometers and form only when temperatures at those heights dip below minus 78 degrees Celsius. They appear to help cause the formation of the infamous holes in the ozone layer by encouraging certain chemical reactions that destroy ozone. Polar stratospheric clouds are also called nacreous clouds. Air is roughly 1,000 times thinner at the top of the stratosphere than it is at the sea level. Because of this, jet aircraft and weather balloons reach their maximum operational altitudes within the stratosphere. Due to the lack of vertical convection in the stratosphere, materials that get into stratosphere can stay there for long times. Such is the case for the ozone destroying chemicals called the chlorofluorocarbons. Large volcanic eruptions and major meteorite impacts can fling aerosol particles up in the stratosphere, where they may linger for months or years, sometimes altering Earth's global climate. Rocket launches inject exhaust gases into the stratosphere, producing uncertain consequences. Various types of waves and tides in the atmosphere influence the stratosphere. Some of these waves and tides carry energy from the troposphere upward into the stratosphere. Others convey energy from the stratosphere up into the mesosphere. The waves and tides influence the flows of air in the stratosphere and can also cause regional heating of this layer of the atmosphere. A rare type of electrical discharge, somewhat akin to lightning, occurs in the stratosphere. These blue jets appear about thunderstorms and extend from the bottom of the stratosphere up to altitudes of 40 to 50 kilometers. Now comes the next layer, which is the mesosphere. The mesosphere is a layer of the Earth's atmosphere. The mesosphere is directly above the stratosphere and below the thermosphere. It extends from about 50 to 85 kilometers above our planet. Temperature decreases with height throughout the mesosphere. The coldest temperatures in the Earth's atmosphere, about -90 degrees Celsius, are found near the top of this layer. The boundary between the mesosphere and the thermosphere above it is called the mesopause. The mesosphere is difficult to study, so less known is about this layer of the atmosphere than the other layers. Weather balloons and other aircraft cannot fly high enough to reach the mesosphere. Satellites orbit above the mesosphere and cannot directly measure traits of this layer. Scientists use instruments on sounding rockets to sample the mesosphere directly, but such flights are brief and infrequent. Since it is difficult to take measurements of the mesosphere directly using instruments, much about the mesosphere is still mysterious. Most meteors vaporize in the mesosphere. Some material from meteors lingers in the mesosphere, causing this layer to have a relatively high concentration of the iron and other material atoms. Very strange high altitude clouds called the noctilucent clouds or the polar mesospheric clouds sometimes form in the mesosphere near the poles. These peculiar clouds form much higher up than the other types of the clouds. The mesosphere, the stratosphere, below it is much drier than the moist troposphere we live in, making the formation of the clouds in this layer a bit of a surprise. Odd electrical discharges akin to lightning, called the sprites or the elves, occasionally appear in the mesosphere dozens of kilometers above the thunderclouds in the troposphere below. Thermosphere. The thermosphere is a layer of the Earth's atmosphere. The thermosphere is directly above the mesosphere and below the exosphere. It extends from about 90 kilometers to between 500 and 1000 kilometers above our planet. Temperatures climb sharply in the lower thermosphere below 200 to 300 kilometers altitude, then level off and hold fairly steady with increasing altitude above that height. Solar activity strongly influences temperature in the thermosphere. The thermosphere is typically about 200 degrees Celsius hotter in the daytime than at the night, and roughly 500 degrees Celsius hotter when the sun is very active than at other times. Temperatures in the upper thermosphere can reach from about 500 degrees Celsius to 2000 degrees Celsius or higher. The boundary between the thermosphere and the exosphere above it is called as a thermopause. At the bottom of the thermosphere is the mesopause, the boundary between the thermosphere and the mesosphere below. Although the thermosphere is considered part of the Earth's atmosphere, the air density is so low in this layer that most of the thermosphere is what we normally think of as the outer space. In fact, the most common definition says that space begins at an altitude of 100 kilometers, slightly above the mesopause at the bottom of the troposphere. The space shuttles and the International Space Station both orbit Earth within the thermosphere. Below the thermosphere, gases made of different types of atoms and molecules are thoroughly mixed together by turbulence in the atmosphere. Air in the lower atmosphere is mainly composed of the familiar blend of about 80% nitrogen molecules and about 20% oxygen molecules. In the thermosphere and above, gas particles collide so infrequently that the gases become somewhat separated based on the types of the chemical elements they contain. Energetic ultraviolet and X-ray photons from the Sun also break apart molecules in the thermosphere. In the upper thermosphere, atomic oxygen, atomic nitrogen and helium are the main components of the air. Much of the X-ray and the UV radiation from the Sun is absorbed in the thermosphere. When the Sun is very active and emitting more high energy radiation, the thermosphere gets hotter and expands or puffs up. Because of this, the height of the top of the thermosphere varies. The thermopause is found at an altitude between 500 kilometers and 1000 kilometers or higher. Since many satellites orbit within the thermosphere, changes in the density of the air at orbital altitudes brought about by heating and expansion of the thermosphere generates a drag force on the satellites. Engineers must take this varying drag into account when calculating orbits, and satellites occasionally need to be boosted higher to offset the effects of the drag force. High energy solar photons also tear electrons away from the gas particles in the thermosphere, creating electrically charged ions of atoms and molecules. Earth's ionosphere, composed of several regions of such ionized particles in the atmosphere, overlaps with and shares the same space with the electrically neutral thermosphere. Like the oceans, Earth's atmosphere has waves and tides within it. These waves and tides help move energy around within the atmosphere, including the thermosphere. Winds and the overall circulation in the thermosphere are largely driven by these tides and waves. Moving ions dragged along by collisions with the electrically neutral gases produce powerful electrical currents in some parts of the thermosphere. Finally, the aurora, the southern and the northern lights, primarily occur in the thermosphere. Charged particles, with electrons, protons and the other ions from space collide with atoms and molecules in the thermosphere at high latitudes, exciting them into higher energy states. Those atoms and molecules shed this excess energy by emitting photons of light, which we see as colorful aurora displays. Ionosphere. The regions of the ionosphere are not considered separate layers, such as the more familiar troposphere, but instead they are ionized regions embedded within the standard atmospheric layers. There are three main regions of the ionosphere called the D layer, E layer and the F layer. These regions do not have sharp boundaries, and the altitudes at which they occur vary during the course of the day and from season to season. The D region usually forms in the upper part of the mesosphere, while the E region typically appears in the lower thermosphere, and the F region is found in the upper reaches of the thermosphere. The D region is the lowest, starting about 60 to 70 kilometers above the ground and extending upward to about 90 kilometers. Next higher is the E region, starting at about 90 or 100 kilometers up and extending to 120 or 150 kilometers. The uppermost part of the ionosphere, the F region, starts about 150 kilometers upward, sometimes as high as 500 kilometers above the surface of our home planet. Before communication via satellites became common, the operators of the radio communication systems often used the ionosphere to extend the range of their transmissions. Radio waves generally travel in straight lines, so unless a tall transmission tower can see the top of the receiver tower, the curvature of the Earth limits the range of the radio transmissions to stations that are not over the horizon. However, some frequencies of the radio waves bounce or reflect off the electrically charged particles in certain ionosphere layers. Pre-satellite radio communications often took advantage of this phenomenon, bouncing radio waves off of the sky to extend the range of the signals. Radio operators had to account for the constant changes in the ionosphere, particularly the shifts or disappearance of the layers between day and night, to effectively take advantage of these mirror-like reflections of radio waves. The ionosphere regions can absorb or dampen radio signals, or they can bend radio waves as well as reflecting the signals as described above. The specific behavior depends on both the frequency of the radio signal as well as the characteristics of the ionosphere region involved. Since the Global Positioning System satellite use radio signals to determine locations, the accuracy of the GPS can be severely reduced when those signals bend as they pass through the ionosphere regions. Similarly, Some radio communications can be disrupted if the frequency used is one that an ionosphere layer dampens or absorbs entirely, resulting in a weakened signal or even total loss of the communications. Scientists constantly measure and produce computer models of the ever-changing ionosphere so that people in charge of the radio communications can anticipate disruptions. Exosphere. The exosphere is the uppermost region of the Earth's atmosphere as it gradually fades into the vacuum of the space. Air in the exosphere is extremely thin. In many ways, it is almost the same as the airless void of the outer space. The layer directly below the exosphere is the thermosphere. The boundary between the two is called as the thermopause. The bottom of the exosphere is sometimes also referred to as the exobase. The altitude of the lower boundary of the exosphere varies. When the sun is active around the peak of the sunspot cycle, X-rays and ultraviolet radiation from the sun heat and puff up the thermosphere, raising the altitude of the thermopause to heights around 1000 kilometers above the Earth's surface. When the sun is less active during the low point of the sunspot cycle, solar radiation is less intense and the thermopause recedes to within about 500 kilometers of the Earth's surface. Not all scientists agree that the exosphere is really a part of the atmosphere. Some scientists consider the thermosphere the uppermost part of the Earth's atmosphere and think that the exosphere is really just a part of the space. However, other scientists do consider the exosphere part of our planet's atmosphere. Since the exosphere gradually fades into the outer space, there is no clear upper boundary of this layer. One definition of the outermost limit of the exosphere places the uppermost edge of the Earth's atmosphere around 1,90,000 kilometers, about halfway to the moon. At this distance, radiation pressure from the sunlight exerts more force on the hydrogen atoms than does the pull of the Earth's gravity. A faint glow of the ultraviolet radiation scattered by hydrogen atoms in the uppermost atmosphere has been detected at heights of 1 lakh kilometers by satellites. This region of the ultraviolet glow is called as the geocorona. Below the exosphere, molecules and atoms of atmospheric gases constantly collide with each other. However, air in the exosphere is so thin that such collisions are very rare. Gaseous atoms and molecules in the exosphere move along the ballistic trajectories reminiscent of the arching flight of a thrown ball as it gradually curves back towards the Earth under the pull of the gravity. Most gas particles in the exosphere zoom along the curved paths without ever hitting another atom or molecule, eventually arching back down into the lower atmosphere due to the pull of the gravity. However, some of the faster moving particles don't return to the Earth. They fly off into the space instead. A small portion of our atmosphere leaks away into the space every year in this way. Modern views regarding the structure of the atmosphere. On the basis of its chemical composition, atmosphere is divided into two broad spheres, homosphere. This is the lower part of the atmosphere, which extends up to a height of about 88 kilometers. It is characterized by uniformity in the composition. The term homosphere means the zone of the homogeneous composition. The homosphere has been subdivided into three sublayers. Firstly, the troposphere, secondly, stratosphere, thirdly, mesosphere. Then comes the heterosphere. The atmosphere above the homosphere is not uniform in its composition. It has a heterogeneous composition, hence the name heterosphere. Different layers of the atmosphere and parts differ from one another in their chemical and physical properties. The heterosphere is also referred to as the thermosphere, for in this layer, temperature goes on rising up to the outermost boundary of the atmosphere. It may be remembered that in the upper parts of the atmosphere, where gases are so rarefied, the high temperatures are caused exclusively by the photochemical actions of the ultraviolet solar radiation. In this sphere, gases are said to be arranged into the following four roughly spherical shells, each of which has its own distinctive composition: nitrogen layer, oxygen layer, helium layer, and the hydrogen layer. The lowermost layer, dominated by the molecular nitrogen, is called, and it's about 200 kilometers above the Earth's surface. Above this layer is the oxygen layer, consisting of the atomic oxygen, whose average height above the Earth's atmosphere is 1,120 kilometers. This layer is overlaid by the helium layer, whose height above the Earth's atmosphere is about 3,520 kilometers. At the top is the hydrogen layer extending up to the outermost boundary of the atmosphere. Nitrogen being the heaviest makes the lowermost layer, and hydrogen being lightest makes the topmost layer. From the foregoing discussion, it is evident that the outermost boundary or the vertical extent of the terrestrial atmosphere is difficult to demarcate. In fact, there is no clear-cut boundary between our atmosphere and the extraterrestrial space. To quote 𝗳𝗍𝗍, there is no atmosphere beyond 32,000 kilometers where the Earth's gravitational attraction is exceeded by the centrifugal force caused by the Earth's spin. The Earth's atmosphere consists of zones or layers arranged like spherical shells according to the altitude above the Earth's surface. Each zone has a unique set of characteristics. For the most part of the layers are not at all sharply defined, and their boundaries are arbitrarily established. That was the lesson on the structure of atmosphere. Thank you and have a nice day.